we are in the 9th lecture. In between, through some survey in the forum and among the TAs, I again came face to face to the fact that mechanical engineering students are not given a numerical analysis course, a formal numerical analysis course, ESO 218 or some such thing, or ESO 208 perhaps. So you may not know many of the basic numerical analysis tools, and this is very bad because that means that you have an option to graduate as an engineer who will not be able to solve uh, an actual problem arising in your field. If the problem was a little complicated, and because for this bad thing, actually we are responsible, we faculty are responsible, because in the tough rivalry among different fields, solid mechanics, dynamics, fluid mechanics, thermal science, this, that, and everything, uh, finally within the number of credits, number of courses, numerical analysis got taught, which is very sad. So it is our fault actually, not yours. Whereas even in my time, in my second class college, when there was no computer in our college, we were taught numerical analysis. Okay, and that basic training helped me later when I got computers in my hand. However, the situation is bad, but the remedy is actually in your hand. Make note that every faculty member of some mechanical engineering subject will not tell you this, but I am telling you because I am concerned about your long-term education and value addition. And that everybody may be, but additionally, I am very aware of the numerical analysis issue. Okay. So remedy is in your hand. Sometime, whenever you get the opportunity, you take a departmental numerical analysis course, ME352T, as an elective, and that will train you in all the numerical analysis tools, which will free you from the bottleneck of not being able to solve actual problems, a step problem in your real issue, which may go a little complicated. For example, as far as nonlinear equations are concerned, quadratic equation is something which you learned in school. And maybe some of you told me that Newton-Raphson method you know. That means one nonlinear equation you can solve. However, a thorough training in that and to be able to solve many nonlinear equations together is something which you should know. That is one. And there are many other techniques, numerical integration. Say you want to evaluate an integral, you want the value, you want to solve a differential equation, you want actual numbers. Okay, so to do numerical integration, to do numerical solution of differential equations, you need numerical methods, and you should have a thorough training. So whenever opportunity arises, I think it will arise in 7th semester. Take this course, ME352T. Okay, numerical analysis course. That's a very good course. Now we come to the issue of our actual course, which we are right now handling. So, solving systems of nonlinear equations is something not very difficult. So, I will tell you the basic ideas of that. And that will be important to solve some of these problems properly, and also to do something in assignment 8, about which one of your friends has started some discussion in the forum. And when I left that issue unresolved, nobody else gave the answer till now. I mean, till whenever I last saw the forum. So let us quickly revisit the previous example, which we said that this is how, which we use as an example of analytical methods. Now, I threw a challenge at you, and one of your big guys gave an outline of the solution, which is by and large all right. But then, if you have gone through it, you would have noticed, and he certainly would have noticed, that it is a lot of, um, I mean, analysis. Too much, too much. And beyond a point, he did not go. He said, now after that, we will eliminate like this and do that, whatever. I also said that. Now, I have done such things, but for just one exercise in one semester course, doing that much is actually a little too much. We should have something sensible. Okay. So we got two vector loop closure equations because two independent loops are there. Resolving which we got four scalar equations in four unknowns, and one variable is given. What next? There are three possibilities of going further. One is there are four equations in four unknowns. Attempt a simultaneous numerical solution of four equations in four unknowns. Make note that they are nonlinear equations. Linear equations, you do it like this. Okay. Four nonlinear equations in four unknowns. To be sure, it can be done, but then there are issues. It's not very easy. It's not child's play. Okay. And wherever the computer solution is taking you, whether it is taking you anywhere, you don't know on the way. So you will see how that happens. Other possibility, which we did, I mean, your friend did, and I supported it, is, and in fact, I told also at the end of the last lecture that eliminate theta 3 from first pair, eliminate theta 6 from the second pair. Then the two eliminant equations you have in theta 4 and theta 5. Okay. The second possibility is that solve not four, but two simultaneous nonlinear equations in theta 4 and theta 5. These nonlinear equations will be a little more complicated than these, but only two, not four, which is one good thing. There is a third possibility, which your friend was attempting, and which is a glorified solution in the literature of 20th century. Okay. So that is eliminate further one of theta 4 and theta 5 to analytical gymnastics. Get a single highly nonlinear equation in one unknown, 8 degree, 6 degree, whatever it is. Your friend thought that it will be 4 degree, but unlikely. Okay. Then one highly nonlinear equation in one unknown you get, and then solve it finally. Now finally, if it is a 6 degree equation in one unknown, how do you solve? You need a numerical method, perhaps Newton-Raphson, or perhaps some more analytical methods to solve polynomial equations, which is a great idea, because in that case systematically you can list out all the solutions, but it goes only that far. Okay. So this is useful, this is elegant, this is great for knowing the structure of the solutions, only for that much. For actually quickly getting one solution, not all 6 or all 8, some of them complex, who knows. It is actually a little overkill. And above 4th degree, even for a polynomial equation, even so-called analytical methods, which take advantage of the structure of the equation, that it is a polynomial equation, not general nonlinear equation, even they are iterative in nature. Beyond 4th degree, you cannot simply solve in terms of radicals. Even 4th degree is quite complicated, though possible. Okay. So, if just two loops, 6-link mechanism has this much of trouble, then imagine what would be the trouble of that earlier problem that we discussed, 11-link 2 degree of freedom 14 joint example of lecture 7, in which in order to outline the steps for a graphical solution, I changed the problem. I said that one input is not known, but one output angle is known. And that way I made it a simple mechanism, not complex anymore. So we will see a better way of handling analytical method. But before that, let us see how do we solve nonlinear equations. This we do quickly because it is not part of theory of mechanisms and machines. And we can do it quickly because it is not very difficult. Newton-Raphson method, which you people have been taught, I don't know in which course, but I guess that if not in the numerical analysis course, which you have not taken, then perhaps in the first year programming course, which is good. Okay. So this is what you will know. Solving a single equation in a single unknown like this. The typical Newton-Raphson equation is this. That is, next iterate is equal to the current iterate minus function value at the current point divided by the derivative at the current point. So the function must be differentiable, which it is in our problem in hand. That is not a problem. So how did Newton or his brother Raphson come to this formula? The basis is in Taylor series. So this Newton-Raphson method basically works on the basis of first order truncated Taylor series. It says that f of xk plus delta x, xk is the kth iterate. That means what you have in hand after k iterations. Initially what you have? Initially you have x0, which is the initial guess. Okay. So Taylor series tells you that fxk plus delta x is fxk plus f prime xk into delta x plus second order term plus third order term and so on. Then you say, very dubious thing, that if delta x is small, then these two terms together, particularly this is of course the value test. So this term will dominate over the delta x squared term, delta x cubed terms, all the time. Why I said dubious? Because for that delta x has to be really small. Okay. Anyway, whether dubious or not, you say that. Then you say that, so for the time being we ignore them. So only these ones. Then you say that xk is a point we have at which fxk is not 0. If it were 0, then we would be done. It is not 0, unfortunately. Now we want a correction in xk such that at the corrected point, function is 0. That will be our solution. So then you say this whole thing should be 0. The moment you say that, you know what is delta x. Because delta x then becomes minus this by this. That is 0. And if this is delta x, then what is the resulting xk plus delta x? That is xk plus this delta x, which is here. So this is the basis of this Newton-Raphson formula, iterative formula. However, since we the dubious, assumption that delta x is small enough that these flows are insignificant. So because of that initial original sin, at that point xk plus delta x, actually f will not be 0. Most probably not, at least not in the initial iterations. So that is why you say that this is not my solution, this is a next iterate, hopefully better. Okay? So hopefully. So when will it be better? And if it is better, then what do you do? Then the way is clear. Then you say that at the next iterate, we do the whole thing for next k and next k and next k. At every step, if f of xk goes on going down, then you are happy. And when that happens, when it works well, then it converges pretty fast. Okay, that is one good thing about Newton's method or Newton-Raphson method. Okay, that it converges fast when it works well, but it may not work well. It does not work well if the derivative is small. If the function graph is somewhere close to horizontal, then what happens is that this is small, so the difference is large, and obviously you will be violating the basic premise that delta x is small. It is a delta x which is magnitude of which is large. Okay, so then you are in trouble. However, for a single equation in a single unknown, there is a safety net. You can say that I will not start with Newton-Raphson iteration till I am in a good position. And how do you figure out whether you are in a good position? At the initial guess, when you evaluate this, if you don't find it small enough, if you find it 778, my God, so big, this is not a good point. So take another point, take another point. And even when you get fx equal to something like 3.2, you don't stop. You say, take another point. Further. When you find that at one x value it is 3.2, at another x value it is minus 2.8, then you know that in between there must be a root. Okay? Because here it is positive, here it is negative, in between there is a root. So this is called bracketing. You can bracket a solution. It is between this and this, there must be a solution. Okay? And then through Newton-Raphson iteration, you start close to the solution by starting within that bracket. That is a good thing. And then another good thing you can do, that in one particular iteration, if you find that Newton-Raphson method is Newton-Raphson iteration is suggesting you an xk plus 1 where the function value is worse than, that is more in magnitude, more than value at xk, then you can have the luxury of not accepting it. I don't take it. And till now, whatever closest to values of fx you have got on one positive side and one negative side, use that as the bracket and bisect the interval. Take the midpoint. So normally you take Newton-Raphson step because that is fast. And if at one particular iteration Newton-Raphson method misbehaves, then that particular iteration you handle by bisection. So changing the point and then start from there. So this way, single equation in single unknown you can handle in some systematic way. A system of equations like this. Now f is bold, x is bold, 0 is also bold. That means they are vectors, okay? Column vectors. You still have systematic way. Again, Taylor series for multivariate functions. Xk plus delta x is equal to fxk plus, now this is Jacobian matrix with ij term equal to del fi by del xj into vector delta x. So vector function value at current iterate plus the derivative, which is now a matrix, derivative of a vector function with respect to a vector variable. Okay. Matrix Jacobian into delta x vector. plus the terms that we are neglecting for the time being. Then you say that we want this capital F to be 0, 0, 0, 0, 0, 0, and therefore this whole thing is 0, vector 0, and that gives you delta x. You say Jacobian inverse value of function negative, and that is this, and that gives you the iteration formula. Again, here also it converges fast when it works well, and does not work well when now. You cannot say that 1 by f prime, because 1 by f prime has been replaced with Jacobian inverse. Okay, that is the multidimensional analog of division. So when you want to divide by something, and that something through this multi-dimension issue becomes no more a scalar but a matrix, then basically rather than dividing, you cannot divide by a matrix, you multiply with its inverse. And that inverse will be troublesome if it is singular or close to singular. Because if it is close to singular, then the inverse will have huge numbers. Okay. And that close to singular is called ill-conditioned. So if this is ill-conditioned, then this delta x, so here there should be an inverse, okay, which has been missed. So this inverse will have huge numbers, so delta x will have huge entries, and that will kill the premise. Not only kill the premise, from a point which is very close to the actual solution, you will make a big jump to Mexico. Okay, so I mean, I am assuming that your original point was not at Mexico. Okay. So that is the problem. And the bad part of it is that in multidimensional problem, where x1, x2, x3, x4, there are several variables, you have nothing to bracket a solution. You cannot have a nice trap, okay, and no bisection, because it is not a scalar interval, it is a region in a multidimensional space. And that also you don't have, because you cannot bracket here positive, here negative. There are other ways of going away this out, this way, that way out. Okay. So that is one problem. That with system of equations, nonlinear equations, you have this issue. Okay. And if unluckily the Newton-Raphson iteration doesn't work, actually for multidimensional it is not called Newton-Raphson, it is called Newton's method for equation solving. If it does not work well, then you don't have a very handy remedy. That is one big issue. That is why whenever you can manage to have a single nonlinear equation rather than two of them or four of them, you should try to have a single one. By that kind of bloody elimination, that's too much. You should have something simpler, straightforward. You deserve it. And let us see how to handle that. And this is where I am very, I would say, aghast that the textbook doesn't mention it, though it says that analytical methods are great and so on. The real greatness of analytical methods is actually not exploited by the typical textbook method. And whereas this is actually not so difficult. The reason is that those whose textbooks we use, the classical scholars, were great, but they were individuals of their time, where the closed form single polynomial equation through elimination was highly glorified, that elegance was really appreciated, and they did not have the idea of the way computer programs operate, the way the artifacts in a programming language operate. They knew it. They did programming, but programming did not sit in their mind the way it sits in the mind of people of your generation who do programming. Okay? So, and at least it should. For example, by function, you should not understand only e to the power x and sin x and cos x and an expression having all these things, a clear cut closed form expression. Only those things are not functions. Functions are quite general. If I give some value of x, if it is scalar variable, then one scalar value. If it's a vector variable, then I give a vector value. Whatever. So some numerical values if I give for x, if there is a rule which gives me matching value of f, always uniquely that I give x, that fellow gives me f. I give another x, that fellow gives me another f. Then it is function enough. And a computer program has a function subprogram like that. You pass a number, and that fellow gives you a number, which is the value of the function. In between, whether it is a simple, straightforward closed form expression or lots and lots of calculations, doesn't matter. It is still a function. And that sense of function you need to utilize here. So a practical approach to utilize loop closure efficiently for a computer program, because at the end you are going to use an iterative method. Okay. And it is better to have a single equation than a number of equations. And it is better to arrive at that single equation without a lot of bloodbaths, okay, of dynastic analysis. So let us see how to do that. First, abandon the illusory elegance of the complete loop closure equations the way we wrote. Starting from O2, coming back to O2. I mean, it's not necessary. You represent all the points, use loop closure in a way, but you do not need to write it all the way around the loop and then eliminate formally the way we did or the way we discussed earlier. Abandon that illusory elegance, which doesn't give you some easy equations to really solve. Okay. Operate in a programming friendly manner from the beginning. And from the beginning, look for one solution, not all the 6 or 8 solutions, perhaps many of them complex. And perhaps many of them, even if real, is not the solution you are looking for. After getting all those 6 or 8 solutions, you have to choose which one I am right now looking for. So, in this, way of working, you look for one solution from the very beginning, selecting the right branch at every intermediate step. Think graphically and work analytically. How? Let us see 2 simple examples quickly. Now I am calling this simple. Okay. Say very simple equation first. Last time in my lecture, I gave you the complete expressions of this. If I am going to solve it analytically, theta 2 given, theta 4 to be found, I don't need to essentially work like that as we did through O2 to O2. Okay. It is not necessary. The equation has value, and essentially, some way or the other, we will be satisfying that equation because there is no other way. But we do not have to do it exactly that way. Let us see how. To begin with, for every point, identify coordinates. That you did in that case also. So initially, you have the coordinates of O2 and O4. Very good. Then theta 2 was prescribed. So based on that, you have the coordinate of this. Coordinates of point A. That is coordinates of O2 plus L2 cos L theta 2, L2 sin theta 2. Great. Now you see, you have 1 point here, 1 point here. Then there is no need to assume a theta 3, assume a theta 4, then write the full equation, then write 2 scalar equations, then eliminate one of the unknowns. All that is not necessary. You know the coordinates of A, you know the coordinates of O2. Now you want to locate the coordinates of B. You can say that I join these two points, A and O4. Okay, that's a line. I can write the equation of that line if I want. Then I say that from that line, I take a single angle, not from the horizontal, but from AO4. And now I know the branch. I know that the point B I want above this line, AO4. So there itself, you can mentally choose the branch. That is, alpha should be positive. Okay, less than 180 degrees. Very good. So if you say that I want this angle alpha or this angle itself, which is there already, if I just take theta 4, theta 3 I don't take from the very beginning. What is the idea of generating two equations and then eliminating one unknown? Generate only one equation. Don't bother about theta 3. Don't bother about any angle here. Theta 4, one angle. Based on theta 4, you can get the coordinates of B. Okay. And then say the distance between A and B should be L3. Single equation. And that is what you got by eliminating, theta 3 from the scalar equations. You squared L3 and L3 cos theta 3 and L3 sin theta 3 and added. That is L3 square you are getting right now, a single equation. So do that. So like that if you do, you will get a single equation in theta 4 and solve it. That you know how to do. Of course, the third problem was easy anyway. However, there is an alternative way also. Do not bother about any angle because you hate cos theta and sin theta in equations. Okay. You say that I have a circle with center A, radius AB. You can write its equation. I have another circle with center O4 and radius O4B, and I am looking for the intersection of these two circles. Two circle intersection is easy. No cos theta, no sin theta. You get two circle equations, subtract them. One of them turns out to be linear. From that, solve y in terms of x, dump it in the other one, and then the other one is a quadratic in x. This is something which you have done many times in school. Okay? And then you get x, which you then substitute in the linear equation for y, get y. So that is how I have outlined it here. So after O2 O4 with theta 2, find out the coordinates of A, then by circle intersection, you would get B, and then from B you get theta 4, simply. Okay? If you rather do the theta 4 way, then you take theta 4 and get theta 4 directly. And based on that, later you can locate B if you want. Okay? So if you try to get the solution for theta 4, you will get two solutions, you will choose one. For circle intersection, you will get two solutions, you will choose one. Okay? So this way, let us try to do in the case of 6 pi, with which we fought with so many equations. Now you say that to begin with, I know the coordinates of O2, O5 and O6. That is the frame. Then theta 2 is given. So I get the coordinates of A. Now I see that BD I cannot find quickly. BC I cannot find quickly. Now make a guess. Make a guess of theta 5. Theta 5. Whatever guess. Okay. 30 degree, 60 degree, 59 degree, 74 degree, whatever you like. Make a guess to start your iterations. Okay. Now, with that guess, now think in the style of a programmer. Right now, simply in the main program, you call Newton-Raphson with the name of a function and this guess value. Now, how does that? Now, this, those of you who know programming, of course, all of you must know programming. You know that this call to Newton-Raphson, this actually Newton-Raphson function itself will have those that Newton-Raphson steps, okay? That sequence of steps, that one iteration, and the value finally. Okay? So, I mean, I have not written the alternative bisection step if Newton-Raphson suggests something bad. Okay, but you can extend it, that call some other function which calls Newton-Raphson, and then if it does not like the Newton-Raphson solution, then it executes a bisection step. That you can write. Okay, that you can cascade. I have written as if every iteration of Newton-Raphson is going to be work fine. Okay, so now you call Newton-Raphson, so that you give a function to get the zero off and the current case value. And based on the current case value, the function actually produces the fx, error at theta 5. So whatever value of theta 5 it gets, so Newtrap will actually make the repeated calls, iteration over iteration. Inside that there will be a for loop or do loop depending upon which language you use. I mean, nowadays I think you people use C or MATLAB, so that will be for loop typically. In Fortran it was do loop. Okay, so inside Newtrap there will be a for loop which will go on calling the function error, and the error function is this: given the value of theta 5, which you have applied here, and other things up to the coordinates of A you already knew. Now with the value of theta 5 known, you get the coordinates of B, and then two circle intersection or whatever way you can get, you fix this dyad. You see, this is what I was saying. Think graphically, work analytically. So this dyad fixing is the graphical thinking, and analytically it means finding the intersection of two circular arcs. Okay. Get B. So from theta 5 get B, from there to arc intersection get B. On the way select the branch. Do not take this one, take that one if you know that is the solution. After you know B you already knew, then C, again select branch, don't take mirror image, okay, and this will be easy. After knowing C, can you say, this C should have been at the given L6 distance from 606, but it is not at L6 distance, it is a little away, and that you find out. 06C for this value of theta 5 you get, and then you evaluate the error. 06C that I have evaluated based on the value of theta 5 minus the given 06C. It should have been 06C, not 06. This is the error. Now this error of theta 5 is the function fx that you want to make 0. So in the Newton-Raphson iteration, that will iterate. Now you see, each of these steps, very simple step. Okay, arc intersection, two circle intersection, very easy. And this will not be even arc intersection if rather than three sides, if you are given this side, and this angle, then it will be even simpler. You do not have to even select the branch with a lot of answer. You know which way the angle is, clockwise or anti-clockwise. That way you will take the angle and just put C appropriately. The moment B is known. Okay? So it is that simple. Two loop equation, two loop mechanism can be solved just like this. And this is with a programming sense. And something like this you will perhaps need to do in the case of the assignment problem, okay, where Sumit said that for the second part, other than B, should you not give me the location of B also? But that shows that till now you have not started thinking of what is a determinate problem in this problem. in this kind of situation. If I give you B also, then it will not be just determinate, it will be over-determinate, in the sense that there will be a scope of conflict then. Because in the first part of the problem, I gave you only B, then I did not give D. Now if I give both independently, then they might conflict. Okay? Suppose I give you a B position also. Then you can fix everything, and on your own actually you can fix the position of B, which is this much below, and I am telling you it is this little below. So there will be a conflict. So that will become overdeterminate. Okay. So the moment you see this kind of a situation, that given value of some unknown, given value of some quantity is suggesting something, and another given value is suggesting something, then there must be a problem. One of the given is actually not given correctly. That is a guess. Okay. So you on your own can take a guess value for the position of B, and based on that you can do something like this. And in the case of that assignment problem, it is going to be easier for you because two of the joints there are prismatic. Okay. Prismatic joints make your life easier. Okay. Now, initially I advertised that big problem, right? 11 link problem. Let us see. The 11 link problem also we can solve like this by formulating a single equation, single nonlinear equation at the end of the day. Let us see how. If you formally write all the loop closure equations, then too many joints, which means too many variables will come into picture, and eliminating, you will go mad if you aspire for a single equation in a single unknown. But the way this would work, I am showing you. I need to make it a little bit smaller. Another little bit of smaller. Yes. Now see. I think you can read it. Okay. Otherwise, you can always open the file and see it big. Okay. So input angles BAC, ABC are given. That is, this angle is given and this angle is given. Okay. And with that, it is a complex mechanism. Make note that with graphical method, we could not handle it. Now, with loop closures, if you write those loop closure equations and then start eliminating, it will be a real help. Okay. Too many variables on the way will come, and you will have your elimination task that much magnified. Now, coordinates of A, B, Y coordinate of point K, you already know. That is the description of the frame. With the inputs given, angle BAC and angle ABJ. Sorry, this should not be ABC, this should be ABJ. Okay, this angle. ABJ, not ABC. Okay. ABC has no identity. ABJ. Okay. So, with these two angles given, 2 degree of freedom, so 2 inputs must be given. C is identified coordinates, and from B, coordinates of J and L also identified because it is a single link. That much is known. So coordinates of coordinates of C, J, and L. C from this angle and JL from this angle, ABJ. Okay. Fine. Now what is the problem? Now you cannot do a dyad assembly because there is no dyad. The closest is dyad. So, according to my prescription, I say that assume one of the strategic ones. Of course, you by now know that if I use this as the strategic one, then it will work because then we could construct it graphically also. But this also would work. Okay. Assume phi, angle ACS. Okay. That is what I am suggesting here. Assume phi. Okay. Guess it. And that is the initial guess for phi, phi 0. Okay. Guess phi. The moment you do that, F would be located, and now you go for the kill. They say that don't immediately determine f. With that guess, enter new trap. Okay. Error function and give this guess value. Just after making the guess, you call Newton-Raphson iteration. Only one I am assuming. That means at the end I will have this Newton-Raphson will be actually solving a scalar function. This one unknown I am assuming, I am guessing. So one error I will get. If I had assumed two, then I would get two errors, two scalar error values. Okay, the error function would be vector. So with this 50 guess, I enter new trap, and new trap will call the error function in order to get fxk and f prime xk. For numerical differentiation, it will call it twice. Okay. Fine, let it do whatever it is it wants. If you don't want it to call it twice, then you will have to supply derivative, which will be troublesome in this case. But with twice calling, it can evaluate the numerical derivative. That is how you have to code new trap. Okay? New trap iteration. Okay. So now this error function. This is the core of the modeling. Your mechanism will reflect in that this error function. New trap is same for all single equations. So based on phi, you get f. That is direct. After getting f, you have already got j. Okay. So f g one link, g j another link. Okay. So you can locate. You have to select the branch above or below. Okay. So select branch. Locate the select branch. Arc intersection. And you have got the numerical values of the coordinates of f, coordinates of j, radius fg, radius jg. You have all numerical values. So you can numerically evaluate it. Inside that function, that evaluation will go on. So g has been found. Once g has been found, this entire pentanary link is a single rigid body. So after g has been found, I will get located because you know the distance fi, you know the distance gi. Okay. I gets located. And branch is obvious because this shape has to be preserved, not the other way around. It cannot suddenly turn around. Okay. So I you locate. And now you say that I am in a position to determine IL. But IL value is actually known. That is a single link. Point L is known because that you got from the input itself. Now you have located I. So you determine IL, and from the given value of IL, within these two you subtract it, take the error. So that's it. You have got the error. IL phi minus IL. And that error now gets returned for this new trap iteration for use. So use that there, and then it goes on. Now after this has converged, that means you have got the correct value of phi. Now use that correct value of phi to locate f correctly, g correctly, I correctly, that you have already done. Okay. Then d also correctly, h also correctly, everything done. Okay. So fgi in a way you have already done. Now locate h and d, and from h locate k, which is very easy. Graphically also it was easy, so analytically even easier. From the location of D, you get the location of E, that is also easy. And from here you get S, and from there you get the distance B. These two might be the outputs wanted. Okay, makes very good sense. So this way you can handle even much bigger problems with several loops. Actually, this problem had 4 loops. Okay, 2 subloops, completely floating loops with no fixed point. However, for solving the problem analytically, you actually did not need all 4 loops all the time. two loops are what is must. But then, since variables would come into picture in large numbers, so you will have to handle them in a very sensitive manner, and for part of it, you might have to make appeal to this forward loop and so on. So, however, for quite complex mechanisms, also, if you select the guessable quantity properly, then you can often make a sequence through which you have to solve a single equation in a single unknown, and that's a great help. Okay? And why I am telling that for very large equations, for very large mechanisms also, with lots of loops, lots of links and joints also, you will be able to handle it with a single equation, because how can somebody make a mechanism with too many loops with large number of links? Because if you try to push a lot of links in one loop, then another loop gets very few links, and that is the loop where you start your operation. Okay, so that is why with the given degrees of freedom, you cannot have loops with large number of links everywhere. If there are some loops which are unduly large, there will be some other loops which will be unduly small, and that's your opportunity. Okay? So this is one way by which you can actually handle large mechanisms with large number of links and joints and large number of loops, therefore, appropriately through analytical methods. Okay? So, but the textbook does not mention it, but you can handle it like this. Okay? So that is important if you try to figure out a practical way of taking full advantage of analytical methods, of the power of analytical methods. Okay, I think I will stop at this point, and next lecture we will take up velocities and acceleration.